if we keep adding together terms of any arithmetic sequence, the answer grows or decreases without limit. The series is called to be divergent. So all arithmetic sequences are divergent. For example, if we start with 2, even if the common difference is as small as 0.01, the series will grow to infinity. If the common difference is minus 0.01, eventually the terms will become negative and the sum will go to minus infinity. So such an arithmetic sequence or arithmetic sequence are divergent in the sense that their sum goes to either plus infinity or minus infinity. This can sometimes happen with geometric series, but doesn't happen always. That's why in this lesson we look at infinite geometric series. Infinite means that we add infinitely many terms. And for example, if we have the sequence 2 plus geometric progression, 2 squared plus 2 cubed plus 2 to the power of 4 and so on, then it's clearly that this will approach infinity when we keep adding numbers up to infinity. And see, I use dots, 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 meaning that I never stop. But it's another story if I start with 1 or even 2, doesn't matter, and then the common ratio will be 1 over 2. See how each term becomes smaller and smaller and smaller. And in fact, there are cases when adding small terms will lead to infinity, but not in this case. So we look now for cases when infinite geometric series have a finite answer. And these sequences are called convergent. When I keep adding many numbers and the answer is finite. So we are going to look at convergent infinite geometric series. Of course, let us start with what we know. And we know the sum of the first n terms of a geometric sequence. So we said that the geometric sequence is u1, u1r, u1r squared, and so on, up to u1r to the power of n minus 1, so n terms. And we saw last time that Sn is, the formula is u1, 1 minus r to the power of n over 1 minus r. We also saw that r is not 1, because in the case r is 1, it's a trivial case, right? So it's not something interesting. If r is 1, then my sequence is u1, u1 times 1, u1 times 1 squared, and so on. So it's a constant sequence, so not so interesting. That's why we don't look at this case, because it's obvious. So we just look at r is not 1, and therefore I can divide by 1 minus r. Now, what happens if I have infinitely many terms? Infinitely many terms will mean if n approaches infinity. So I have infinitely many terms. And really, I need to look only at this term here. Because in the formula, n doesn't appear anywhere else. So see, u1 and r are constants. So the big question is, what happens with r to the power of n? R to the power of n for different values of r when n approaches infinity, when n gets bigger and bigger and bigger. Example, if r is 2, I will get 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 1,000, to the power of million approaches infinity. But if r is 1 over 2, I'm going to get 1 over 2, 1 over 2 squared, 1 over 2 cubed, and so on, and see how it approaches 0, because the numbers get smaller and smaller. And if I multiply by a half every time, the number gets smaller. What happens, for example, if r is negative? So that's a question we're going to answer. So in order to explore what happens, I use this app, GeoGebra, which is a very cool app. So what I'm doing is that I will be defining a slider which will act as r, because I want my r to change. And I want to see what happens if r is negative, if r is positive as well. So I just do between -5 and 15 with a small increment, with a small step. So that's my r from here. I want to explore r to the power of n. And then in GeoGebra, I need to put x for the function. So I put r to the power of x, not of n, because that's how my software knows it. Yeah, so it's r to the power of x. So I want to see what happens when this x gets very, very big. Let's stop a bit and analyze r equals 1.4. So 1.4 to the power of 1 is 1.4 squared, cube, and so on. And see, 1.4 to big powers gets very, very big, going to infinity. And it's something we know, that we keep multiplying by a number bigger than 1, the result gets bigger and bigger and bigger. So r to the power of n will approach infinity for r bigger than 1. When n approaches infinity. So my question is, what happens when n approaches infinity? And in my file here, x acts as n. Yeah, okay, so let's continue. What happens now if r gets smaller? So if r is less than 1. Okay, so if r is less than 1, see, r became 0.9. And see how immediately, if you multiply by a number smaller than 1, the result gets smaller and smaller and smaller. So for r between 0 and 1, then r to the power of n will approach 0. Now the question is, what happens if r is 1? If r is 1, we are going to get an uninteresting case. So we said that we don't look at that. What happens if r is smaller than 1? Well, that's interesting, because my software can't deal with this. It can't do negative to a power of x where x is any number, but let's think ourselves. So if r, for example, is 1 over 2, we said that 1 over 2 to the power of n approaches infinity when n gets bigger and bigger. What happens if r is negative 1 over 2? What happens to negative 1 over 2 to the power of n? Oh, sorry, approaches 0. We said, yeah. Okay, what happens to negative 1 over 2 to the power of n? Let's give n values. So for n equals 1 is going to be minus 1 over 2. And then it's going to be 1 over 2 squared, minus 1 over 2 cubed, 1 over 2 to the power of 4, minus 1 over 2 to the power of 5, and so on with alternating signs. So think of a graph. Minus 1 over 2 plus 1 over 2 squared, minus 1 over 2 cubed, plus 1 over, and so on. So see, the terms alternate above and below the x-axis, but they will approach 0 from both sides. So in this case, this will approach 0 as well. And as you can imagine, this happens for all numbers between negative 1 and 0. So we have the following cases for now. If r is bigger than 1, then r to the power of n is infinity. If r is between minus 1 and 1, then r to the power of n approaches 0. Now think what happens if r is smaller than negative 1. Like, for example, negative 2 to the power of n is going to be negative 2, 2 squared, negative 2 cubed, plus 2 to the power of 4, negative 2 to the power of 5, and so on. So it will approach either plus infinity or minus infinity. It depends if the terms are odd or are even. So this sequence also is divergent. I even can say that it approaches infinity because it goes either to plus or to minus infinity. Same not a nice case is when r is negative 1, because your sequence is negative 1 to the power of n. So it's negative 1, 1, negative 1, 1. So C doesn't stabilize, it alternates. This means that we came to the main conclusion of this section. R to the power of n will approach infinity for r bigger than 1, 0 for r between minus 1 and 1, 1 for r equals 1, but we said it's not an interesting case, and is divergent. I mean, I can say that it approaches something for r smaller or equal than minus 1. Therefore, look at Sn, the sum of the terms of a geometric series, 1 minus u1 times 1 minus r to the power of n over 1 minus r. This one converges only for r between minus 1 and 1. And S infinity, the sum of infinite number of terms, remember for this r, this one is going to converge to 0. So therefore, S infinity is going to be u1 over 1 minus r. And this is our main result today. That's when an infinite geometric series converges. And that's the sum. On the next pages, I'm going to solve a few questions. Please read each question and stop the movie and try it yourself. Next question, please pause the movie and try it yourself.